All right, next up, Sutter from IBM, who will talk about circuit cutting.
Okay, thank you, Michael. Thanks, Robert. So this second last talk. Hopefully it's not too long and not too technical. And if you have questions, then just ask immediately. So I wanted to give it on the blackboard, but there's no blackboard maybe. So therefore now you have to read my poor handwriting. I apologize for that. So I present here like some old series of work. So if somebody has seen it already, then again, I apologize, but has at least something to do with near-term computing. So I hope it fits into the conference schedule. And this joint work with Christoph, Lucas is somewhere here, and Lucas. And so the idea is a very practical one, but I hope we will also touch some more fundamental or information theoretic arguments that justify why this problem is maybe interesting. And so the idea is, I call it circuit cutting, but maybe in a more general way, it's just understanding how you can do non-local computation locally. And this will be relevant, hopefully, in the future when we build larger quantum computers. Then at some point, at least for the roadmap or the vision IBM has and others in superconducting qubits, at some point you cannot make the local processors larger anymore unless there's like new technological progress, because I was told of the wiring, you cannot control all the qubits anymore. So what they plan is to fit a couple of hundreds, maybe thousands qubits on a chip and then stack different chips together, which then they link with quantum links, such that you still can do universal computation. But of course it will be then expensive in a certain sense to like do a gate between qubits that are on different QPUs, on different chips. And so this is then of course a problem that it's not maybe for us to solve it, but maybe for like people that write compilers or other things to somehow, I don't know, compile a certain program in a way that it's good for the hardware. And so maybe circuit cutting or understanding how local or how we can map a certain circuit or certain computation to a certain hardware structure, this could be interesting and relevant in the future. But of course we cannot do it for free, and I would like to understand, okay, what are the fundamental limitations? Okay, and so, okay, you could in the meantime see the picture. So a very similar picture would be just we have a non-local circuit. Locality is here like the gray area and the blue area. This is our bipartition. And then you see that we have like 3 gates which are non-local in this definition, the yellow ones. And we are just asking whether we can replace this circuit here with this circuit here, such that we get the correct outcome. So it's important. So we do not want to have like errors. And what is also important is that we only consider circuits where we consider an expectation value in the end. Okay. And so, okay, so the first thing, or the most important thing is maybe first. So whenever you hear something that this can be done for free, this cannot be true in full generality, right? So we need to be aware, and this was made formal, I think, in the very early days by people like Charlie Bennett and others, that of course such things like doing non-local computation locally is not for free. It will scale exponentially in n. And the very hand-wavy argument is the following. So if it would not scale exponentially, right, then we could just decompose an arbitrary quantum circuit into small pieces, run the small pieces 50 qubits or something on a local computer, and then stack it together without a big overhead, and so quantum computing would be meaningless, I would say. And of course you can make this rigorous, but okay, just that you are aware, okay, it will scale exponentially. And exponentially in the number of cuts in this case we do. If we cut n gates, then we need to expect cost or overhead, I will specify this, that scales exponentially in n. Okay, so the informal result is that also, I think yesterday was mentioned that of course in asymptotics the problem is solved, scales exponentially. But maybe in practice, the asymptotic answer is not always the full answer, because we will not be in an asymptotic setting, at least not for the next couple of years, or maybe never. So it still makes sense to quantify what are the precise or the quantitative costs. And so, so we do this for a couple of gates. For example, if we cut n CNOT gates in a worst case setting, then we say the overhead scales as 4 to the n. Of course, this is terrible scaling, but just to give you an impression what we aim to quantify. So we really aim to quantify here the basis of the exponential scaling. Of course, makes a difference, because if this basis is 1.00001 to the n, then it's maybe not so bad, despite it's an exponential scaling. Okay, how is this done? So this is done by a technique that maybe most of you have seen it at some point. I think was borrowed from classical computer science, I was told, and it's called quasi-probability simulation. The idea is, in some sense, nice, but it's also very, very simple. So the idea is that we have, like I explain it here in simple terms. So we have an operation, I call this E here, can be a unitary, for example, a C0 gate, that we would like to perform, to run. But we cannot do it. But instead we have like a set of operations, I call them Fi here. These are operations we actually can run. So in our setting we have a non-local gate as E, and we have local, like single qubit operations that we can run in our resource theory, that are certain operations that are for free, or we can do them. And now if we manage to decompose, like to write the operations, the operation E as a linear combination of the operations Fj, so importantly here this AI is really a linear combination, so this can be real numbers, can be negative. It's important because otherwise it's very restrictive to find such a QPD, so quasi-probability decomposition. So suppose we can write this, then we can convince ourselves that we can like construct the unbiased estimator. Okay, what does this mean? So this is the expectation value we would like to evaluate, but again, we cannot evaluate it directly because we cannot run the operation E. But instead we have this quasi-probability decomposition, so this linear combination, so we just plug it in here. And then we see that we have like a linear combinations of expectation values we can run on our hardware, which are these guys here. Then we can do a little reformulation, so we just introduce PIs in this sense, and we introduce a constant kappa, which is the one norm of our coefficients. And then we can just rewrite it like this. This is really a basic rewriting here. And then you see you have a Monte Carlo type algorithm. So with probability Pi, I pick an operation Fi, I evaluate this expectation value, I classically post-process the outcome with this constant here, with this number, and I get an unbiased estimator. So I get the true expectation value. Right. So now, okay, it's time to pause for a second and think about this. So, okay, we have the correct expectation value, but there's a cost somewhere. And the cost is that we have the true expectation value, that the random variable at the outcome of the measurement has the correct expectation value, but has a larger variance now. Of course, in practice, if we want to compute expectations values, we set a certain accuracy, and then we use a Höfting bound or something, and then this determines how many shots we need to do such that we are in this accuracy with high probability or certain confidence. And now if you have a larger variance, this means to have the same accuracy, we need to do more shots, right? And this is the overhead. And so the overhead is quantified by this constant kappa here, so the one norm of the coefficients. This makes actually quite a bit of sense if you think about it, because, okay, when is this one norm large? It's large if many of the coefficients are negative in some sense, right? Because usually these operations here and these operations are trace preserving maps. So if you put a trace around them, so we still should have one, so the AIs, they sum up to 1, right? So if none of them is negative, the one norm is 1, right? We have no overhead. So in other words, if we can write our operations that we cannot run here as a convex mixture, or convex combination of operations we can perform, we can use the probability, quasi-probability simulation, which is then a probability simulation. The word quasi is because it has negative coefficients, then we can use it without any overhead. But this is also not the interesting case, because interesting is the case where we need the negative AIs to make this identity here even possible. Is this clear? Okay, so okay, again, so the one norm of the coefficients is the overhead, or it's like the variance. If you make it more precise, okay, didn't make it fully precise. So the variance scales as this kappa, as this one norm of the coefficients. So we would like to find the best decomposition here, or the decomposition that has the smallest possible L1 norm. Okay. Maybe last comment is, of course, I now explained this for one operation we cannot do, but now suppose we have a circuit with many operations we cannot do, we can just apply this principle for every single gate we would like to replace, and then the total sampling overhead is just the product of the individual overhead. So this is nice because we can just scan through our circuit in a somehow local way, and every gate we would like to replace, we just pick it and then we just sum up everything. And so the total overhead like then scales exponentially in n. Right. Okay, so again, what I said before is this is actually the main quantity of this talk. So this is, I would say, using this quasi-probability simulation method, this is the optimal sampling overhead. It's just maybe a bit complicated optimization problem where we just try to find the quasi-probability decomposition, so this linear combination that has the smallest possible one norm of the coefficients. And of course we can now define it with respect to certain set S here, which are the operations that we can run. So this can be, for example, local operations in a cutting setting, or LOCC, local operations in classical communications, for example. And so this optimization problem, if you stare at it, you probably already see that it doesn't look so easy. I mean, of course, depends highly on the complexity of the set S, but it also has some non-linear. So we optimize here over the AIs and the FIs, and there's also product here, so it's not totally trivial, this optimization. Okay, maybe before I go back to the one, here's just the overview slide for those that are maybe familiar with the method. So this has been used in many many situations, but 3 of them are probably well known. So one idea is that we have we would like to run an ideal noise-free gate, but we only have noisy gates available. Then we can use this method, and it is known as probabilistic error cancellation. This is an error mitigation type technique. We can also have the ambition to run an arbitrary gate, but we only can do Clifford gates, for example, because the Clifford gates are the ones we can simulate efficiently on a classical computer. So this then gives rise to all these classical simulation algorithms that have been pioneered by Sergey and others. And so there you see also the overhead then scales in the number of T-gates, so in the number of gates we need to replace with this method. And so in this talk, said it already, so we have non-local gates, for example, a C0. In the following, I only focus on the C0 for simplicity, and we can do local gates, which in this case is single qubit gates. Okay, and so the goal is just to solve this optimization problem for the C0. Maybe for LO and LOCC. This is a bit random, but I would argue it's the 2 sets that are practically relevant, because LO would mean if we decompose a circuit with LO, we can use a single hardware, single computer, and run all the individual pieces on the same hardware. LOCC would mean that we have 2 hardwares that we use in parallel, and they can exchange classical information. So these are 2 settings that are maybe reasonable. And so the theorem is that the optimal decomposition has an overhead, like gamma factor, some people call this, which is 3 for the C0. Of course, this is quite large, and it's maybe disappointing, but you should also keep in mind that the C0 is, in some sense, the worst possible gate to cut, right? Because it creates a lot of entanglement, right? You can create a bell pair with a C0, and so therefore cutting a C0, we cut always in the worst possible situation, is probably expensive. And maybe if there's time in the end, I can show you some other gates that create less entanglement, where the gamma factor is then much smaller. For example, if you have a controlled rotation gate with a small angle, then hopefully the overhead is also small if the angle is small. Okay. Still everything clear? Yes?
Is there a good intuition for what is large or small when looking at this gamma? What would be very
yeah, okay, I mean, what is large and small is, I mean, can I make, but somehow what would be nice is that somehow, I mean, okay, if you have a constant, the constant is even large, it's probably quite restrictive, right? Because 3 to the n, you can plot it and this gets gigantic fast, right? And it's really so, the intuition is really, if you cut then these gates and you want to have a certain accuracy of your expectation value, you need to run 3 to the n more shots. So now you can play a bit around how long you're willing to wait, right? But 3 to the n, I don't know, it's pretty hopeless, I would say. But for example, there's some, so Aram Harrow had a paper where he tried to use these cutting ideas for Hamiltonian simulation application, where the application was such that you have to cut through many controlled rotation gates, and the angle, it had lots of very small angles. And then if you cut many angles that are very small, then you can cut a gigantic number of angles with still having a very low overhead. Or for example, another application that somebody told me is like the quantum Fourier transform. Quantum Fourier transform has tons of controlled rotation gates with very, very small angles. So cutting a QFT is actually very cheap. So it can be even constant if the angles decrease. I mean, you could also imagine scenarios where the angles get smaller and smaller if the size gets larger, so this can balance out. But I'm not sure these are the really interesting scenarios. Okay, let us quickly go through this proof, not in full generality, but just to give you a flavor. So to get like, okay, this is an identity here, so we need to prove an up on the lower bound. So to show that the gamma factor is smaller or equal than 3 is in some sense easy, but can also be hard, but it's just because it's a minimization problem, right? You give a protocol or a quasi-probability decomposition which achieves an overhead of 3. For the CNOT, there has one been proposed by 2 Japanese researchers. They didn't know that this is the optimal one, but they proposed a method to decompose it, and it turns out they achieve 3. So now the other point which I like a bit more is like the more information theoretic argument, which is the converse, right? To showing you cannot do better than 3. And so, okay, how can you do this? You can do this by remembering, okay, what is the choice state of a unitary? So choice state is defined here. You probably all know it. We have 2 bell pairs entangled between A and A prime, B and B prime. We send it through the unitary. We get here a state, which is the bell state, choice state. And now we can convince ourselves that this inequality here is true, so that the gamma factor of the unitary is larger or equal than the gamma factor of the choice state. Okay, why is this the case? This is the case because you can see here in this diagram that if we have axes, I mean, if we can simulate the unitary, we can create the choice state with this protocol here. So therefore, the overhead for doing the unitary in a LOCC way cannot be smaller than creating the choice state, because we can just run this protocol. Now, okay, I didn't explain what is the gamma factor for a state. I only explained it, what is it for a map, but you can imagine it's the same, right? For state, it's just a state preparation idea, right? We have an entangled state here, and we would like to write it as a linear combination of product states. Right? And we can ask, okay, what is the optimal, what are the smallest possible coefficients that we can do this? Now, for states, it's actually what makes this proof work. For states, it's actually much easier to analyze the gamma factor. So the gamma factor for states is in a one-to-one relation with an entanglement measure called robustness of entanglement, for those that know. But it doesn't matter so much what it is. It's just an entanglement measure that has most of the nice properties entanglement measures have. So why is this fact actually reasonable? So it's reasonable because we can consider the 2 extreme cases. So suppose rho AB is not entangled, so it's separable. Then we can, by definition of a separable state, we can find coefficients AI, which are non-negative, right? Convex combination. So then the gamma factor is 1. And the gamma factor is 1, then this means the entanglement measure, should be also 0, right? Because it's not entangled. It's a reasonable entanglement measure, so that's okay. If we now have a state that is highly entangled, maybe a Bell state or something, then the entanglement measure here is maximal, and then the gamma factor is large. Right? Okay. And what is also nice is that, as for many entanglement measures, in general, it's hard to compute robustness of entanglement, but for the special case where the state is pure, it's simple. There's a formula in terms of the Schmidt coefficients, so we can just read it off. Okay, so okay, we can read it off. Okay, left here some space. We can read it off. So compute the choice state of a C0 gate, the Bell state. We can read off here the formula. Okay, it's a bit fast, but believe me, this is then 3, right? So we actually completed the proof. It's 3. So we have up on the lower bound that achieves 3. I didn't explain it in full detail, but we can discuss it later if you're interested. Now, okay, now we understand the gamma factor for one C0 gate. So the next question that you could ask is this gamma factor multiplicative under tensor products or not? Or maybe in a more less mathematical or more like how do you say, less technical description? Is it cheaper to cut 2 C0 simultaneously than to cut twice a single C0? And okay, of course, this inequality is always true, right? This is the trivial direction because we can just use the decomposition for one C0 and just apply in tensor product. But maybe there's a strategy that is doing better for 2 C0s. And so let's analyze this. Okay, spoiler, this actually turns out to be strict, so it's not additive or not multiplicative under tensor products. And so how can we analyze this? We can analyze it by remembering that actually in a LOCC resource here, or in a LOCC world where all the LOCC operations are for free, a Bell pair is actually equivalent to a C0. Okay, what do I mean with this strange equivalence? I mean, okay, the 2 settings, right? I can create so one here says that I can create a Bell pair if I'm giving a C0 gate, right? Just by this little simple circuit that everybody knows. So this actually shows that actually with a C0 I can create a Bell pair. So actually, in some sense, this inequality maybe is true. Now, is the reverse also possible? Yes, it is possible by a famous protocol from Gottesman and Zhuang called gate teleportation. Okay, this is a complicated circuit. If you haven't seen it, you don't need to fully understand it. But what it's doing, it's usually this wiggly line here is a Bell pair. And then everything that is afterwards is just LOCC protocol with this locality structure. So everything above the red line is, let's say, partition A, everything below is partition B, and there's only classical communication between the parties. So actually, because this is a C0, which is proven in the gate teleportation paper, it's not super complicated, but it's a nice observation to observe this, then this actually tells us that if we have a Bell pair, we can also create a C0 with LOCC. So it's actually then this inequality here, and therefore we have an equality here. Okay, so this actually means that if you're in a LOCC setting, we can just focus on the task of preparing Bell states, and then we can use gate teleportation to convert this into C0s, right? So we just need to use the QPD method to prepare Bell states. And so now, as we've seen before, preparing one Bell state, the cost is free. We just plug it in, we use the formula that relates gamma to entanglement, robustness of entanglement, and robustness of entanglement can be read off in terms of Schmidt coefficient, so it's free. Now we can say, okay, what is the cost of now preparing 2 Bell states? So 2 Bell states, this is, of course, it's small or equal to 9, but it turns out that it's actually 7. And the intuition is that now here we have a locality structure just between A and B. But here in 2 Bell states, right, we have this Bell state, okay, probably you cannot read my ugly handwriting. This is on A1, B1, and this is on A2, B2. The global locality structures, A is now A1 tensor product A2, and B is B1 tensor product B2. So we can, of course, use protocols that use entanglement between A1 and A2. It's not clear that this is helpful, but as the formula suggests, it is helpful, or proves actually, it is helpful for the task. So basically this means preparing 2 Bell pairs simultaneously is considerably cheaper than preparing twice a Bell pair. Then the same goes for C0s because we have gate teleportation. Okay, and then you can analyze this for n Bell pairs and everything. So maybe I already wrap up, and then I have an open question that I want to ask. Maybe this is the most interesting thing from the talk. So we understand how to cut, we understand the gamma factor for Clifford gates. Okay, why do we understand this? Because for Clifford gates, gate teleportation works. So this not only works for CNOT gates, but it works for general Clifford gates. And the resource states that you can use to teleport it is always the choice state. So therefore we understand this. We also understand how to cut arbitrary 2-qubit gates. This is a bit more complicated, but it uses like a so an arbitrary 2-qubit unitary has like a special decomposition, which is called KAK decomposition. And then you can use this very specific decomposition to actually construct a protocol that you then can prove is optimal. But for larger unitaries, we are screwed. And it's not only us, I mean, it's like also people like Aram Harrow and others, they tried, they can only do the 2-qubit case. So for higher qubits, you cannot, you don't know how to optimally cut it. Now you could say, okay, is this relevant? Because I can decompose an arbitrary unitary into single qubits plus CNOTs, for example. So in some sense, it suffices to cut a CNOT, but this is, I mean, for cutting perspectives, you should never decompose stuff. You should use it as it is. I mean, the example is, suppose again you have a controlled rotation gate. Then the gamma factor, okay, this falls into this category. So it's like, it's small if the angle is small, believe me. But if you now decompose this into a CNOT plus single qubit gates, then suddenly the overhead is gigantic because it's the CNOT is 3, right? So you should never decompose stuff. So it's actually quite interesting to understand arbitrary unitaries, but we do not. Okay, so maybe, okay, let me end with the question that I had. Maybe some of you know it. So actually it has to do with gate teleportation. As you've seen in the talk, gate teleportation is very useful to understand the cutting or the non-local implementation of unitaries, because we can then work with states. And states are much, much easier to handle than the unitaries. Now, okay, if we know gate teleportation, we can swap between unitaries and states, as I said. But now, sadly, we only understand it for Clifford gates. So I would like to understand it for non-Clifford gates. And the question would be the following. So suppose I have a non-Clifford unitary here. I would like to find a protocol, that an LOCC protocol here, that implements this unitary with a resource state that I call here psi. And of course I want to have the optimal resource state. Okay, what does optimal resource state mean? I want a resource state that is somehow in correspondence with the entangling power of a unitary. Again, the special cases are the following. So if the unitary is not entangling at all, the resource state should be not entangled. If the unitary is highly entangled, like a CNOT, the resource state has a lot of entanglement in terms of a Bell state, right? Of course, I'm aware of some works, maybe from Jens or some others, that say, okay, you can always use a Bell pair to then implement any 2-qubit unitary, to teleport any 2-qubit unitary. But of course, this is very wasteful because I want to have the optimal resource state. The Bell pair is clearly not optimal. I mean, with 2 Bell pairs, I can teleport any unitary, but I want the best possible state in some sense. And so what we do know is that for non-Clifford gates, it's not the choice state. So you can prove that, I mean, naively, you could hope for that the same protocol that works for Clifford gates just also works for non-Clifford gates, just nobody could prove it so far. But this is, okay, maybe this is also common knowledge, I don't know, but this is clearly not the case. You can rule this out by proof. But I don't know actually what is the optimal state here. So you need to have more entanglement somehow, but I don't know what it is. If somebody knows, I think this would be interesting. It's not only interesting for cutting. I was told by IBM people that also the way they would like to implement like gates between these QPUs, as I said at the beginning, is that you do it via gate teleportation, that you actually distribute entanglement between the non-local things, and then it's like measurement-based computing. So it's actually something that's maybe getting more relevant than we thought maybe 10 years ago. Okay, thank you.
Great, thanks, David. I think we still have time for 1 or 2 questions.
So did I see correctly that like the optimal cost then if you do n CNOTs was 2 to the n
That's right.
Okay.
That's right.
But I mean, this is outside the LOCC framework, but do you also know what then the cost is, sort of the circuit cost within, you know, A and B? So I'm thinking of this as a sort of practical protocol. If I now have to go and prepare fairly complicated entangled states to do this, you know, like if your FIs that you have to prepare are get more and more complex as n grows, then it's no longer very useful. From
I agree. I mean, I agree. Like this. Okay, it's maybe a good point that you touched. Like from a practical point of view, of course, if you want to use this sub-multiplicativity, the cost you pay is that the operations you use to run, like these FIs, as I call it, they get very large, right? I mean, they use, if you have like 4 C-nodes, for example, that you would like to jointly cut, then the operations work on 4 qubits, right? And of course, if you make it larger and larger, then it's even more. So the good thing is, didn't explain it, that somehow the convergence to 2 is quite fast. So the formula is here, right? So in practice, I could imagine that you just, suppose you have like 100 qubits, 100 C-nodes you want to cut, then there's no need to like do the FIs on 100 qubits. You would probably do blocks, like I don't know how large you want to do this, but this, I mean, you can plot this function, this converges quite fast to 2, so, but you're right, I mean, it's an important point.
Thank you.
Yes.
Yeah. Sorry, I think that, okay, in the interest of time, I will pass over.
Yes, so I was just wondering, does it help in any way to also consider complex quasi-probability distributions and optimize
Yeah, that's a
over
good
those?
point. Okay, I was told, but I didn't convince myself that it doesn't help. Because doesn't help. But okay, I have to, never convince myself. I'm just hope it's correct.
Maybe as our next speaker slowly makes their way to the podium, we could take one last question.
About the last part that you mentioned regarding non-Cliffords.
Yes.
Could we like start off from a model where we can control the non-Cliffordness by, let's say, doing t-doping and then seeing what we get as the optimal state? I mean, as a heuristic, to see how how this state required scales with, let's say, the amount of non-Cliffordness in that unit tree which needs to be decomposed.
Yes, maybe. Sorry, I don't know.
Awesome. Well, let's thank David again for his great talk.
Willst du den